These are the sort of scales you used to encounter in most shops. This time, I'm going to be looking in some detail at the use of digital measurement systems in connection with weighing machines. And later in the program, we return to KEF to look at the use of similar systems in the design of loudspeakers. All the way through, I'll be emphasizing analog to digital conversion. Right, let's start at the beginning, scales. First, let's examine the traditional device. For our pound of sausages, the scales provide us first with the weight, here, but they also provide us with additional information. Look here. If we select a particular price, say for convenience 60 pence a pound, then by finding where this strip intersects with the weight, we find the total price. In our case, 62 pence. Although this table simplifies the calculation of total price, there obviously isn't enough room for all the possible prices. For example, in this area, all prices are to the nearest pence, whilst in this area, they're to the nearest halfpence. We say that these scales have a resolution of a halfpence and 1 pence respectively. The accuracy of these scales tells us whether a measured pound is really 16 ounces and not 15.5 or 17.25. And it's important for you to distinguish between a system's resolution and its accuracy. Now, let's think how we might design a digital machine that weighs and shows the total price. With these scales, the weight is shown across here, and the price up here, and our total price is derived from the table. So the central feature of a digital weighing machine could be a ROM-type lookup table. We could enter the weight and the price per unit weight into the ROM, use it as a lookup table, and derive the total cost. But where do we get the weight and price from? Well, the price is a number, so we could use a keyboard to enter it directly. That's not a problem. But the weight is an analog quantity, so we must first convert it to digital. My reason for choosing the weighing machine example is that there's a close analogy between analog to digital conversion and weighing with the old balance type scales like these. Let me show you. With these scales, what I do is to compare an unknown weight, my sausages, with a set of known weights, just like the analog to digital converter. In the converter, we compare the analog input with a known digitally generated voltage by means of a device called a comparator. But with the scales, I do the comparison. So let's put some weights on. They're about a pound, so I'll start with that. Well, that's not quite enough, and 17 ounces is just too much. So the actual weight must lie somewhere in between. I can't get a better measurement because the smallest incremental change I can make is my 1 ounce, and it's called the quantization interval. It determines the measurement resolution. In terms of the A to D converter, it corresponds to the voltage represented by the least significant bit. The comparison is never exact. There's always an error. It's the quantization error. No matter how small we make that quantization interval, there will always be a small error. Right, now we seem to be equipped to deal with a digital design. In fact, it's a schematic, but it should provide you with the basic idea. We have the scales here, spring-loaded in our case, like our first example. And they're connected to turn the potentiometer. And that gives us an input voltage to our A to D converter. So the weight has been binary coded, and that acts as an input to the ROM. The cost input to the ROM is derived from the keyboard. And the total cost appears as the output from the ROM. Right, now let's see if we can improve the design. Well, first, this ROM will be very large because of the number of price options we want to put in and the number of weight options. For example, to duplicate the first set of scales would require in excess of 4,000 locations. Well, we can improve things by recognizing the operation of the ROM. It's multiplying weight and price. So we can replace the ROM with a digital multiplier. In practice, this spring and potentiometer arrangement will be replaced by a strain gauge, but this is adequate for our purposes. Well, now let's have a look at the real thing. First of all, the keyboard. I can type in the unit price, and that appears here. Now, if I put on a weight, that appears here, and the total price, the product of these two, appears here. Notice that it takes a short time for the weight to settle. This is because the input to the A to D converter oscillates. Something like this. The overshoot is determined by the amount of damping in the system. The converter samples this waveform continuously. And because the oscillations die out, we end up with a fixed value for the weight. So sampling this form of waveform is no problem. But what about non-decaying AC signals? There are a few pitfalls, and I want to show you them. Let's examine a sine wave using this digital oscilloscope. The oscillator is providing the input, and the input is sampled at a constant rate, and the sample stored in a digital memory. I can display those samples on the screen, and if you look, you can see the samples. They're the little horizontal lines. And to make the display somewhat easier to view, they're joined up by straight lines. Let's now increase the frequency, keeping the sampling period fixed. As I do so, you can see that we're slowly decreasing the number of samples per cycle. And then we get to a point where it's not really clear because we haven't got enough samples. But watch what happens as I continue to increase the frequency. We get to the point where suddenly we start getting more samples per cycle. So, increasing frequency with a fixed sampling period, something odd has happened. And that jittering is also due to the sampling process. And if I wanted to take a measurement, I can store it like this. But let's just confirm what's happening. I'll come back down in frequency this time. I'll just release the store. Now, as I decrease the frequency, we have fewer samples per cycle. And then we gradually get to the point where we start increasing the number of samples per cycle. Obviously, something's wrong. Let me see if I can show you on the drawing board. Here we have amplitude plotted vertically and frequency horizontally. And this is a linear frequency plot, not the usual log type. Now, what we observed was that at high frequencies, the oscilloscope indicated a low frequency. Now, I made some measurements earlier in the day, and what I found was that the generator, reading about 4 kilohertz, produced a measurement on the oscilloscope of about 1 kilohertz. Now, let me see if I can show you what's happened with the aid of this half-silvered mirror. You're now looking from this side, and you can see that as I move the mirror backwards and forwards, there is one position at which the image of this predicted frequency exactly overlaps that of the measured frequency. And the position of the mirror at this point corresponds to a frequency of half the sampling rate. There it is. And so this measured frequency is in fact wrong because the signal was not sampled fast enough. Remember, the sampling rule says we must have at least 2 samples per cycle. This measured frequency is called the alias of the actual frequency as given by the oscillator. Well, to see the effect of aliasing, have a look at this power spectrum. Note that there is significant power above half the sampling rate. If I put the mirror up again at the frequency corresponding to half the sampling rate, you can see what's going to happen. the power in this area is going to be reflected back into this area. So the measured power spectrum will look something like this, without those components and with that power added up here. If this happens to a real signal, it will introduce errors into the measurement. That's why anti-aliasing filters are used to minimize such errors. Well, we've had a brief look at A to D converters and the sampling of analog signals and seen how they can be combined in a digital weighing machine. Now, let's extend some of these ideas to some of the measurement problems you met in TV5, and in particular to the technique of impulse testing.
Well, as you may have guessed, we're back at KEF Electronics, and this time we're going to look at their computer system and see how they use it in quality control of stereo loudspeaker systems. But before we go on to that, let's just recap a little. Remember in program 5, we were concerned with taking a drive unit and combining it with a filter so as to limit its response to a portion of the audio range. And then we would take the bass unit, the high frequency unit, and the mid-range unit and combine them together to get a satisfactory frequency response across the whole range. But there's one point we didn't mention in that program, and that is for a stereo system, you need 2 loudspeakers. And they have to have matched frequency responses. Now, there are 2 ways you can measure a frequency response. You can use a sine wave, rather like you did in the home kit, or you can use an impulse test and a computer. This company have decided to use a computer, and I'll let Raymond Cook, the managing director, explain why.
The acoustical characteristics of loudspeakers have traditionally been measured in terms of frequency using a variable frequency generator of sinusoidal waveforms as a signal source. Curves such as this, which are fairly typical of this kind of measurement, in fact show the transfer function of a particular drive unit plotting sound level against log frequency. The equipment for doing this kind of work is relatively inexpensive, but it does need a very special environment in order to give highly accurate results. We really need a silent room completely free from reflections over all the audio frequency band. But this, of course, is impossible to achieve in practice, and the best we can do is never quite good enough. Moreover, these special test chambers are very expensive and cannot be easily moved, so they're not really suitable for a production environment. By contrast, impulse response measurements can take place in ordinary rooms, provided that these are large enough. The captured impulse responses can be signal averaged to improve the effective signal-to-noise ratio, and the stored impulses can be used as a basis for calculating the frequency response, the phase response, and other data of interest to loudspeaker designers. And it's convenient to do this in digital form using mini computers.
Mr. Cook's talked about KEF's computer system. Well, here it is. Basically, this is the computer, display unit, analog input, and the keyboard control. And here, the disk unit for mass storage. This is the display terminal. We've talked about impulse testing and the idea of a pulse, and this is used because of its spectral content. Let me show you what I mean. This is the basic pulse. Its width is about 10 microseconds. Plotted voltage against time, and the total time duration here is about 2 milliseconds. Now, we use the Fourier analyzer to show the pulse spectral content. This is a logarithmic scale and log frequency. You can see that for much of the spectrum, the output is in fact flat. And the pulse is equivalent to exciting a speaker with all the sine waves simultaneously. But one measurement gives us the complete response. So that's what impulse testing means. Let's go back to Mr. Cook.
Now, although Fourier analyzers are still relatively expensive, they cost approximately 10 times equivalent analog measuring equipment. They are nevertheless a cheaper proposition than the old analog setup because we no longer need the special measuring environment. Moreover, the equipment is very flexible and can be moved readily to any new part of the factory, so it's very suitable as a production tool. The data is easily stored, doesn't deteriorate on storage, and can be recalled at will many, many times and displayed in many forms, such as the amplitude frequency response, the phase frequency response, cumulative decay spectra, Nyquist diagrams, and so on. We can also plot useful data such as histograms for production control. This computerized equipment is particularly effective when it comes to grading and matching units in order to make a very precise and accurate loudspeaker. This would be a daunting task in the old analog form because, you see, we have to consider not only variations in sensitivity, but also the variations in general response shape and small accidents to the frequency response over localized areas. This, as I say, would be virtually impossible in the analog form, but is relatively easily coped with in digital form using mini-computers.
Now, let's look at a speaker test. This is the impulse response of the speaker. You can see that it's rather noisy around the 0 volts level. And this is basically because a narrow pulse doesn't enable us to get much energy into the speaker. But we can get over that problem by averaging lots of impulses together. Let me show you. In this case, we've averaged 4 impulse responses together. The advantage is that the impulse response occurs at the same point in time for every measurement, but the noise doesn't, and so it gradually subtracts out. And in this case, we've got 64 averages. The noise is virtually gone. Now, there are 2 things to note about this response. The first one is that the impulse response doesn't occur at 0 time. This is because there's a delay for the sound to propagate from the speaker to the microphone. This introduces a slight error in the phase measurement, and so it's normal to shift the impulse response back to 0 time. Well, this is the shifted impulse measurement. The second point to note is this area. This is caused by reflections within the room, and if we want an accurate measurement, we have to remove those reflections. Well, this is the final impulse measurement. Average of 64 individual measurements, and the room reflections have been removed. We can use the Fourier analyzer to calculate the frequency response for the speaker. Again, we've used a dB scale and log frequency, and you can see that over most of the frequency range, the response is fairly level. Well, that's the impulse testing. Let's go over to Glyn, who's actually on a production line, to see this system in use.
This is the final test and assembly area for the loudspeaker systems. The computer produces information which says which of the drive units have to be put together to make a matched loudspeaker system. And that's done down at the end there. After the final assembly, they move along the conveyor belt to the diagnostic center here. And what's done here is a simple swept frequency test. So let's try it. That one seems okay. So from here, they move along to the entrance of the test chamber. First of all, they're checked for alignment, and they go into the test chamber for the final impulse testing. From here, the speaker moves on for final inspection and packing. And this completes the use of the computer in the assembly work. But the computer system has other uses in quality control.
We've been able to use the computer to spot variations in diaphragm materials. For instance, woven textiles, which are used in the manufacture of soft dome tweeters, can often give response variations due to minor differences in the resin content. In the ordinary way, this would be extremely difficult to trace and pin down. But by plotting the histogram of frequency response for a very large batch of units, we were able to show that in some parts of the frequency range, the variation in sensitivity was extremely small, as signified by this tightly bunched characteristic here. But at other parts of the range, the spread was relatively large. This enables us not only to identify precisely where the trouble is occurring, but also to monitor and control the improvement as it comes along.
Well, Mr. Cook's just explained about the use of computers in quality control, but there's one other use that I couldn't go without showing you, and it's to do with cabinet design. When we excite a drive unit, the cabinet walls move, something like this. And we can use the computer to measure that motion and display it in a graphical form. Have a look. This is an exaggerated three-dimensional display showing cabinet wall motion. Using the computer in this way, it's possible to design better cabinets.
$800.